The name of the module is Sufficiency. In the present module, we are going to discuss the idea of sufficient statistic. A statistic capital T will be called sufficient for an unknown parameter theta if it contains all informations about theta that can be obtained from a sample. In other words, a sufficient statistic summarizes the whole data. It plays a very important role in the theory of statistical inference. First, we shall define a sufficient statistic. Then we shall discuss how one can obtain pseudo-random number from a distribution. That is, one can obtain a random sample by using a sufficient statistic. Some examples will be discussed in this connection. Our objectives are to explain the concept of a sufficient statistic for a parameterized family of distributions, to illustrate through examples how sufficiency can be thought of as a data reduction technique, to briefly introduce the notion of a minimal sufficient statistic. Let x1, x2 up to xn is a random sample from a population with PMF or PDF f theta. The sample can be represented by a vector x equals to x1, x2, xn that takes values in the set script x equals to set of all small x1, small x2, small xn such that product over j from 1 to n f theta xj greater than 0, that is the joint PMF is or the joint PDF is greater than 0. Here theta is the unknown parameter. It may be vector valued or real valued. Here we write theta equals to theta 1, theta 2 up to theta d is the unknown parameter, taking values in the parameter space script theta. Script theta is a subset of the d-dimensional real line. A sufficient statistic for theta is a statistic that in some sense captures all the information on theta contained in the sample x. Here x is a vector x1, x2, xn. In other words, if a statistic capital T equals to t is a function of x, tx is sufficient for theta, then after having observed t, it is not possible to get any additional information about theta from the sample. That is, t contains all the informations about theta. Now we define a sufficient statistic. A statistic capital T, which is a function of sample observations x1, x2, xn, is said to be sufficient for theta, or rather for the family of densities script f, which is equals to set of all f theta such that theta belongs to script theta. If the conditional distribution of any other statistic, say t star, given t is independent of theta for all possible realizations of t. Now we make some remarks. First, if capital T is sufficient for the family script f, then T is also sufficient for the smaller family script f star, which is equals to set of all small f theta such that theta belonging to a parameter space script theta star. Here script theta star is a subset of script theta. Now there is an equivalent definition of a sufficient statistic. A statistic capital T is said to be sufficient for theta if the conditional distribution of x1, x2, xn given capital T is independent of the parameter theta for all possible realizations of T. Actually, this definition comes from the previous definition by taking the other statistic T star as the whole data x1, x2, xn. So, the two definitions are equivalent. Now, we make another remark. A sufficient statistic T contains all the information on theta in the sense that from the knowledge of T alone, it is possible to generate by some random mechanism a random quantity y, say, which is completely equivalent to the original x. That is, the distribution of x is the same as the distribution of y. As x and y have identical distributions, each of them depending on theta, they provide exactly the same information about theta. That is why we say that there is no loss in information. This is not difficult to justify. We show for the case when the random variable x has a discrete distribution. We take any particular value of x, say small x belongs to script x. Now, probability under theta capital X equals to small x. This is equals to probability under theta x equals to small x intersection T of capital X equals to T of small x. This is due to the fact that x equals to x implies Tx equal to Tx, and hence we get probability x equals to x given Tx equals to Tx into probability Tx equals to Tx. It follows from the definition of conditional probability. Now, the distribution of x given T is independent of theta, and therefore, the first part we can write probability y equals to x given Tx equals to Tx into probability under theta Tx equals to Tx, and hence we get probability under theta y equals to x intersection Tx equals to Tx, and therefore we finally get probability under theta y equals to x. Hence x and y have the same distribution. We consider a very simple example. Let capital X be a single observation from a normal population with mean 0 and variance sigma square, where sigma greater than 0 is unknown. Let Tx equals to mod x. Given mod x equals to T, the only possible values of x are plus T and minus T, and by symmetry of the distribution of x, the conditional probability associated with each is half. Thus, the conditional distribution of x given mod x is independent of sigma. Hence, T equals to mod x is sufficient for sigma. Now, it is to be noted that given the value of the sufficient statistic mod x, we can generate a random variable y with the same distribution as x through some random mechanism. We toss a fair coin and we define y equals to minus of mod x if the toss yields a tail, equals to mod x if the toss yields a head. Here mod x is the actual observed value of x. Then it is very easy to show that y follows normal 0, sigma square, and hence y and x have the same distribution. We consider another example. Let x1, x2 are independently and identically distributed Poisson lambda random variables, where lambda greater than 0 is unknown. We consider the statistic capital T equals to x1 plus x2. The conditional joint distribution of x1, x2 given x1 plus x2 equals to T is given by probability under lambda x1 equals to x1, x2 equals to T minus x1 divided by probability x1 plus x2 equals to T. It is valid when small t equals to x1 plus x2 and is equals to 0 otherwise. Thus, for small x1 equals to 0 to t and small x2 equals to t minus x1, we get the conditional joint distribution as probability x1 equals to x1 intersection x2 equals to x2 given x1 plus x2 equals to t is equals to t choose x1 into half to the power t, as probability x1 equals to x1, x2 equals to x2 given x1 plus x2 equals to t is independent of lambda. The statistic t is sufficient for the parameter lambda. Now, given the value of the sufficient statistic capital T, we can generate a random vector y1, y2 with the same distribution as the original observations x1, x2 through the use of the following random mechanism. We toss a fair coin t times, where t is the observed value of capital T, and define y1 and y2 be respectively the number of heads and the number of tails obtained. Then the distribution of y1, y2 will be same as that of x1, x2, and hence we have no loss in information. Now we consider an example. Let x1 and x2 are independently and identically distributed Poisson random variables, each with parameter theta, where theta greater than 0 is unknown. We consider the statistic capital T equals to x1 plus 2x2. Now we calculate the conditional distribution of x1, x2 given T. We calculate probability under theta x1 equals to 0, x2 equals to 1 given t equals to 2. This is given as probability under theta x1 equals to 0, x2 equals to 1 divided by probability under theta x1 plus 2x2 equals to 2. Note that the event x1 plus 2x2 equals to 2 can occur in two mutually exclusive ways. One is x1 equals to 0, x2 equals to 1, and the other is x1 equals to 2, x2 equals to 0. Since x1 and x2 are independent, we finally get the conditional distribution as theta into e to the power minus 2 theta divided by theta into e to the power minus 2 theta plus theta square into e to the power minus 2 theta divided by 2, and it finally boils down to 2 by 2 plus theta. Clearly, the conditional distribution of x1, x2 given t equals to 2 depends on theta, and hence t is not sufficient for theta. We consider our next example. Let x1 and x2 are independently and identically distributed Bernoulli random variables, each with parameter theta, where theta belonging to the interval 0, 1. We consider the statistic t equals to x1 plus 2x2. Note that the possible realizations of t are 0, 1 and 2, and probability t equals to t when t equals to 0, probability t, and therefore t equals to 0 can occur in only one way. When x1 equals to 0, x2 equals to 0. T equals to 1 can occur in only one way, x1 equals to 1, x2 equals to 0. And finally t equals to 2 can occur only in one way, x1 equals to 0, x2 equals to 1. Each possible event corresponding to exactly one possible realization of t. And therefore, given t equals to small t, each of the above events either happen with conditional probability 1 or not. In symbols, probability x1 equals to 0, x2 equals to 0, given t equals to 0 is equals to 1. Probability x1 equals to 1, x2 equals to 0, given t equals to 1 is equals to 1. And probability x1 equals to 0, x2 equals to 1, given t equals to 2 is equals to 1. Since the conditional distribution of x1, x2 given t is independent of the unknown parameter theta, here t is sufficient for theta. We proceed to our next example. Let x1 and x2 be independently and identically distributed random variables, each with common PMF fnx equals to 1 by capital N if x equals to 1 to capital N, 0 otherwise. This is called discrete uniform distribution. Here the random variable x1 and x2 can take the values 1 to n each with probability 1 by n. Here the unknown parameter n can take some positive integral values. We consider a statistic capital T x1 x2 equals to maximum of x1 and x2. The possible values of t are 1, 2 up to capital N. For any mass point small t belonging to the interval 1, 2 up to capital N, probability under n t equals to small t is actually equals to probability under n t less than equals to small t minus probability under n t less than equals to t minus 1, and probability under n t less than equals to t is equals to t by n whole square. Similarly, probability under n t less than equals to t minus 1 is also equals to t minus 1 by n whole square, and thus we get probability under n t equals to small t is equals to t square minus t minus 1 whole square divided by n square, and hence the conditional PMF of x1, x2 given capital T equals to small t is probability x1 equals to x1, x2 equals to x2 given t equals to t. This is actually probability x1 equals to x1, x2 equals to x2 divided by probability t equals to t, when the maximum of small x1, x2 equals to t, and it boils down to 1 by t square minus t minus 1 whole square, when max of x1, x2 equals to t is 0 otherwise. And we see that here the conditional distribution of x1, x2 given t equals to small t is independent of n, and hence t is sufficient for n. But if we take the statistic t1 which is minimum of x1, x2, then t1 will not be sufficient for n. We demonstrate this by taking any particular mass point t1 which is actually 1 to capital N. We have probability under n t1 equals to t1. this probability can be calculated as probability under n t1 greater than equal to t1 minus probability under n t1 greater than equals to t1 plus 1, and probability under n t1 greater than equal to t1 is equals to n minus t1 plus 1 by whole square by n square, because t1 greater than equal to t1 can occur only when each of x1 x2 can take the values t1 t2 t1 t1 plus 1 up to capital N, and similarly probability t1 greater than equal to t1 plus 1 is equals to n minus t1 whole square by n square, and thus we get probability under n t1 equals to t1 is equals to n minus t1 plus 1 whole square minus n minus t1 whole square whole divided by n square, and the conditional distribution of x1 and x2 given t1 equals to t1 is given by probability x1 equals to x1, x2 equals to x2 divided by probability t1 equals to t1, and this is equals to 1 by n minus t1 plus 1 whole square minus n minus t1 whole square if minimum of x1 x2 equals to t1 and is equals to 0 otherwise. And we see that here the conditional distribution of x1 x2 given t1 equals to t1 depends on n, and hence t1 is not sufficient for n. We consider another example. Suppose x1 and x2 are independently and identically distributed random variables. Each follows normal distribution with mean theta and variance 1. Here theta belonging to the real line is the unknown parameter. We consider two statistics. One is t is equals to x1 plus x2, and the other is t1 equals to x1 plus 2x2. Then the joint distribution of t and t1 is bivariate normal with parameters 2 theta, 3 theta with mean 2 theta and 3 theta, variances 2 and 5 respectively, and with correlation coefficient 3 by root 10. The joint distribution will follows from the fact that the distribution of any linear combination of t and t1 is univariate normal, and so the joint distribution is bivariate normal. From the theory of bivariate normal distribution, we know that the conditional distribution of t given t1 equals to some tau is normal with mean 3 tau minus theta by 5 and variance 1 by 5, whereas the conditional distribution of t1 given t equals to small t is normal with mean 3t by 2 and variance half, and therefore we see that the conditional distribution of t given t1 depends on theta, but the conditional distribution of t1 given t is independent of theta. That means when t1 is known, there will be some information about theta left in the distribution, and therefore t1 is not sufficient for theta. On the other hand, if t is known, there will be no information about theta left in the distribution, and therefore t is sufficient for theta, but t1 is not. Finally, we discuss some idea about a minimal sufficient statistic. Actually, the concept of minimal sufficiency will be discussed broadly in a later module. A statistic, capital T, is said to be a minimal sufficient statistic for theta if number 1, t is sufficient for theta, and number 2, t is a function of every other sufficient statistic. In other words, a minimal sufficient statistic provides the greatest possible reduction of the data, as the following example shows. Let x1, x2, xn be independently and identically distributed random variables. Each follows normal with mean theta and variance 1, where theta is the unknown parameter, theta belonging to the real line. we consider n statistics T1, T2, Tn, where T1 is the whole data set x1, x2, xn. It is an n-dimensional statistic. T2 is of dimension n minus 1. T2 is a vector with elements x1 plus x2, x3 up to xn. T3 is a statistic. It is of dimension n minus 2. It is a vector with elements x1 plus x2 plus x3, x4 up to xn. And finally, Tn is a one-dimensional statistic. This is just summation over I from 1 to n xi. It is very clear that Tj is a function of Tj minus 1 for every j, that is T2 is a function of T1, T3 is a function of T2, and finally Tn is a function of Tn minus 1. And hence Tn provides the greatest reduction of data, and therefore Tn can be considered as the minimal sufficient statistic for theta. In this lecture, we have seen that a sufficient statistic contains full information about an unknown parameter theta, in the sense that given the value of the sufficient statistic t, the distribution, the conditional distribution is independent of the unknown parameter theta. We have also seen that given the value of the sufficient statistic t, we can generate a random variable x prime which has the same distribution as the original random variable x. In the next module, we shall discuss a method for obtaining a sufficient statistic, that is called Fisher-Neyman factorization theorem.